plus ax plus
Again, we have to do it one more. It will what?
One second. They have to do so.
I think it just.
That's right.
Why now? I think it just.
one of the classical problem in algebraic number theory is if we have given a monic irreducible polynomial fx with integer coefficient and a root theta, when we can say that the field q theta is monogenic. Since this question is very hard, we can ask the smaller approachable questions like when k equal to q theta and ak is the ring of integers of k, then when z theta will be equal to ak, or when are the certain primes which cause obstruction to homogeneity of K. There has been done a great amount of work in this area, but there is still much to do. Coming back to the first question, when AK is equal to Z theta, in 2015, Joran and Khanuja proved this for the special type of fx when fx is x to the power n plus ax plus b. They proved that if we take k equal to q theta and theta have minimal polynomial fx x to the power n plus ax plus b over the field q, then ak will be equal to z theta if and only if for each prime p which divides the discriminant d of fx satisfies one of the following conditions. First, when p divides both a and b, then p square should not divide b. Second, when p does not divide ab, then p square does not divide the discriminant of fx, which is b. Third, when p divides a and p does not divide b, then from the formula of discriminant, we can say that p will divide n in that case. So if we write k as the highest power of p, which divides n, then either p square divide and p does not divide b1, or p square does not divide a and p does not divide a to the power n, b plus minus b1 to the power n, where a2 is a to the a by b and b1 is minus b to the power pk plus b by p. Fourth, when p does not divide a and p divide b with l as the highest power of p which divides l minus 1, then either p divides a1 and p square does not divide b, or p does not divide a1 and p does not divide a1 to the power n minus 1 plus minus b2 to the power n minus 1, where b2 is b by p and a1 is minus a to the power b to the power l plus a by b. Now we have the result by Talbot that any polynomial x to the power n minus x minus 1 over q is irreducible. So this corollary is a quick consequence of the above theorem, that if a equal to q theta with theta satisfying x to the power n minus x minus 1, then ak will be equal to z theta if and only if this term n to the power n minus 1 minus n to the power n minus 1 is careful. Now, in 1962, Stan proved that the discriminant of the trinomial x to the power n plus ax to the power m plus b is this. Then, keeping in mind this formula, in 2017, Kaur, Khanuja and Sangwan extended the result of Khanuja and Joral to the trinomials of the type x to the power m plus ax to the power m plus b. Now, they proved that ak equal to z theta if and only if for each prime p dividing b satisfies one of the five conditions. These were the conditions reduced by them. This is the picture of Thakur, Khanuja and Sangwan. Now, when we move from trinomials to quadrinomials, there has been some little amount of work done in this direction. In 2022, Anu Thakur proved that if fx of the type x to the power n plus ax to the power n plus bx to the power n minus 2 plus c with degree greater than or equal to 3 over q, with the condition that a square is equals to 4b and GCD of a comma n is 1. Then we consider its root theta and have the field k equal to q theta. Then in this case, ak will be equal to z theta if and only if for each prime p dividing the discriminant d of fx, either p does not divide c and p square does not divide d, or p divides c and p square does not divide c. Now, if we talk about our second question, when are the some price causes obstruction to the homogeneity of the field K? I will first define the definition of a common index divisor. A prime P will be called a common index divisor of the algebraic number field K if P divides the group index AK is to Z theta for every algebraic integer theta that generates K. That means if K is equal to Q theta and theta is an algebraic integer, then P will divide AK is to Z theta. Now, Delkai was the first who proved the existence of common index divisors. He showed that for the field Q theta, where theta satisfies x cube minus x square minus 2x minus 8, in that case, 2 will be a common index divisor of K. He proved that by showing that in this case, the prime group splits into 3 distinct prime divisors in AK. So, in this type, we can say that the common index divisors are the prime that can split too much over polynomial factorization of finite fields. This was the result by which we can conclude that Delkai proved that if K is an algebraic number field and P is a rational prime, then P will be a common index divisor of K if and only if for some positive integer f we have number of distinct prime ideas of K which lies above P and have residual degree h. This term is greater than the number of monic irreducible polynomials in FPX of degree h. Since we can count the number of monic irreducible polynomials of degree h in FPX, to show that a prime is the common index divisor, we just have to find out the number of distinct prime ideas which lies and have lies over P and have residual degree h. Now, I will define the definition of index of a number field. Index of the number field is defined as the GCT of the group index AK is to Z alpha, where alpha is an algebraic integer which generates the extension K. So, what are prime common index divisor? Prime common index divisor are basically the prime factors of this IK. We can easily see that if we have AK equal to Z theta for some theta algebraic integer, then we have IK equal to 1. But its converse is not true. That is, if we have IK equal to 1, we cannot conclude that AK will be equal to Z theta for some theta in AK. In 1907, Kaur proved this important theorem, which says that if we have a rational prime P and a positive integer n with P less than n, then there will exist an algebraic number field K of degree n in which P will be a common index divisor of K. 6 years later, Zelinsky proved the necessity of this condition. He proved that if prime P can be a common index divisor of an algebraic number field of degree n if only if P is less than n. So this is a very important result. To find the prime common index divisor of a number field of degree n, we just have to consider only those prime which are less than the degree of n. In 1930, Angstrom studied the prime power decomposition of the field index IK. After that, Nakahara studied the index of non-cyclic but abelian biquadratic number fields. In 1991, Kaur and his research group characterized the field indices of biquadratic number fields which have Galois before. In 1983, Lorente and Nat proved that in the field fq plus px plus q with p odd q even, the two-eddy valuation of 4pq minus 27q square even, and this term, odd part of this term is converted to 1 mod 8, then when 2 will divide IK. After that, Davis and Spielman in 2018 was they have successfully generalized this result to the this field x to the power 4 plus ax plus b. Keeping in mind the result of Zelinsky, we can see that in this case 3 can also be a prime common index divisor. So they have given the necessary and sufficient conditions for prime 2 and 3 to divide the field index IK. What we have done, we have considered the field K equal to Q theta, where theta satisfies the polynomial fx, x to the power 5 plus ax plus b. We have considered this polynomial irreducible. then we know that discriminant of this polynomial is this. We have proved that for any odd rational prime, P does not provide a group index ik. That means any odd rational prime P cannot be a common index divisor of P. For proving when P is strictly greater than 5, we have used the map. We have proved it with the help of fundamental equality and didn't use the previous methods. And for prime 3, we have done a separate case by considering the primordial factorization of 3. The second theorem states the necessary and sufficient condition for the prime 2 to divide the field index ik. We have also given the primordial factorization of 2ak. These were the results proved by us. Now we can see that if none of the conditions A7, A9, A13, A15, A18, A19, A21, A22, A24, and A29 hold, then keeping in mind theorem 1.1 that a odd prime cannot be a prime common index divisor, we can conclude that ik will be 1. This is the example. In this case, we fix our A and B such that valuation of A is 0 and valuation of B is 1. A is congruent to 1 mod 4 and B is congruent to 2 mod 4. So by case A15 of theorem 1.2, we can conclude that 2 divides ik, thus ak will not be equal to z theta for any algebraic integer theta. These are the references. The results are in paper 3. This paper has been accepted for publication in proceedings of the Edinburgh Mathematical Society. Thank you.
Any questions or comments?
Yeah, I was wondering, you have conditions, now suppose you just computed for A and B, let's say each going from 1 to 1,000. I was wondering